Alright, hello everyone, and in this video we're going to take a look at area between curves. Let me get my digital pen going here. So the concept here in this section is really an extension of what you would have learned in a Calc 1 class. So we're going to look at area between curves. So maybe as a quick refresher of here for a couple minutes, right? Let's talk about area under a curve, what you typically maybe saw in a Calculus 1 course. So in the Calculus 1 course, you may have considered some function y equals f of x, and what you would have been interested in, let's say, is the area bounded by the curve and the x-axis. So we might have been looking for that region there. All right, now remember, our approach to this, excuse me, our approach to this would have been, let me see if I can redraw this real quick, right? Our approach to this would have been initially to use what we call approximating rectangles. So we might have picked a specific point here. Well, actually, let me draw this, right? So we might have picked, here's one rectangle, and then here's another rectangle, and then here's another rectangle. And I want to point out to you, for all of these rectangles so far, between this x value and this x value, right, we called that our delta x. And then I used the left endpoint to come up to find the height of that rectangle. Then for this interval of x values, I use the left endpoint to come up and find the height of the rectangle, and so on and so forth. Now, in a Calc 1 class, we might have used the right endpoint of each of those rectangles. We might have used the midpoint of each of those rectangles. The way that I'm drawing all of these, I'm using left endpoint. Now, dot, 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 we may have stopped right here, and we used, let's say, like n rectangles, right? So again, we would find like the area under those rectangles. So typically we wrote it this way. We would say something like the area is approximately the sum of, we're going to sum up all of those rectangles. So what we normally did, right, if this was the first rectangle, second rectangle, third rectangle, out to the nth rectangle, we would typically say, well, we're going to take the ith rectangle and we're going to let I go from 1 to n. So we'd sum up the n rectangles. So remember, technically we're finding, let's say, the area inside that rectangle, right? So the area would be the width of the rectangle, which is the delta x, and then it would be the height of the rectangle, which is the function value at that endpoint, right? So our height. So this is how we would typically introduce the concept of integration in a Calc 1 course, and we would call this a Riemann sum, or in other words, what we would really do is say, well, to find the exact area, we're going to let the rectangles become infinite. So again, I'm going to, if this is 10 rectangles, that's going to give me a good approximation. If this is 20 rectangles, that's a better approximation. If this is 50 rectangles, 100 rectangles, the more rectangles that we use, the better. And if we let the number of rectangles go to infinity, then we're going to get the exact area under the curve, right? Now, some textbooks will say this. They'll say n goes to infinity, or they'll say delta x goes to 0, right? Because if you think about that picture for a second, as I squeeze more and more rectangles in here, this delta x right here is going to get smaller and smaller and smaller. So some textbooks write the notation that way. And then this is what we call the Riemann sum, which we write the summation as an integral, and we're saying basically here's the heights of the rectangles, here's the widths of the rectangle. Right, now normally we're talking about area under some particular finite interval, right? So normally we would say, okay, here's a, the beginning of the function, here's b, right? So we would have kind of a left endpoint and a right endpoint. So in integral notation, we would write from a to b, and we would call this a definite integral. Right, so in Calc 1, this was how we wrote the area under a curve. So under, again, meaning between the function and the x-axis. What we want to do here is just extend that concept, and we're basically going to look at area we're going to look at area between curves. So let me try and draw this picture again real quick. So let's say we have a grid, and then let's say we have an upper curve here. Let me use green. here's an upper curve, let's call this f of x, and then here's a lower curve, let's use red. All right, let's say here's a function g of x, and we want to find the area between those curves. Right? So in other words, we're finding, let me use this color here, I think that's gray. Right? We're finding the area between those curves. Right? Well, look, it's same concept, right? So what we're going to do is squeeze in rectangles under there. And if I look at this particular rectangle with a width delta x, I come up to my function, right? And I'm really just finding this area here. Right? So what I'm really doing is finding, the distance between those two functions. Right? If you think about this for a second, if I look at an x number line, how do I find the distance from 3 to 10? Well, we subtract, right? 10 minus 3 would give me the distance there. So I'm basically doing the same thing. I have the further distance minus the closer distance. So if I think about the area of that one particular rectangle, right, it's the kind of the upper curve minus the lower curve. So we're going to have the upper curve minus the lower curve, and that's going to give us the area between the functions, times the thickness, right? So again, area of a rectangle would be thickness, my delta x, times the height of the rectangle. Again, I don't want the entire height up to f of x, I want the height trapped between the two. So that's going to be the f of x minus the g of x gives me what's left, right? And again, technically, we're going to sum these up from 1 to n, and we're going to say our area is approximately that value, and then when we take a limit of that expression, that's going to give us our integral. All right, so we're going to say the limit is n goes to infinity of the sum from 1 to n of f x sub I minus g of x sub I, right, times the width. Right? And, again, let me remind you, notationally, some textbooks say, well, as we get more and more rectangles, our delta x goes to 0. So that gives us the integral of the upper curve minus the lower curve from A to B, right? So again, I want to point out to you what I just said verbally a couple times, right? This is like the upper curve right here. This is the lower curve, right? So the f of x, this is like upper curve minus lower curve. That's what we're talking about there, all right? So there's our quote-unquote formula, if you will, to find the area between two curves. And it doesn't matter where this region lives. Right? This region could live in quadrant 1, quadrant 2, quadrant 3, quadrant 4. It could live over all of the quadrants, right? We could have, something like this. We could have the upper curve be, let's say, here. And we could have the lower curve, let's say, be here. Okay? Doesn't matter how it's oriented. We're still going to have upper minus lower for our rectangle. All right? Keep that in mind. So with a translation, we could make that connection. Right? So let's take a look at a couple quick examples here. So let's say the first example we consider is we want to look at the area bounded between, let's say we have y equals 12 minus x squared. And let's say we're looking at the curve y equals x squared minus 6. So again, I just want to talk about skill-based question here, right? So let's say we're going to find let's find the area bounded by these curves. All right, look, I could lean on some technology to graph this, but let's just talk about for a moment. We have the skills to graph these functions. So what do we have here? We have a parabola. It has a negative leading coefficient, right? So it's going to point down. And then if I set x squared minus 12 equal to 0 to find the x-intercepts, right, I'm going to get to x equals plus or minus the root of 12. right? What's that? Let's see, root of 16 is 4. Root of 9 is 3. So this is somewhere between 3 and 4. Let's say right there, right? 1, 2, 3, 4, somewhere between 3 and 4. Rough sketch, right? If x equals 0, y equals 12 is the y-intercept. So roughly something like that. There's my f of x, or my 12 minus x, right? I didn't use f of x there. Right? All right, and then let's look at y equals x squared minus 6. Right? So what's the graph of this look like? So here's a parabola that opens up, and it's shifted down 12 units. Right? So parabola opens up, and it's shifted down 6 units. Sorry. All right, shifted down 6 units. And I didn't give myself enough room to graph here. I apologize. So shifted down 6 units, look roughly something like that. Okay. All right, you know, I actually could have graphed this parabola in that same manner. I made that a little bit more difficult than I really needed to, right? This is negative x squared shifted up 12 units. I made that a little harder than I needed to. Now, so, all right, the instructions here say find the area bounded by the curves. So what we're really looking at here is between this intersection point and this intersection point, or what's the area bounded between those curves. So just like we talked about, you know, in words a couple minutes ago, I'm going to look at the upper curve minus the lower curve. That's, in essence, what we're going to consider here. So we're going to have the integral of the upper curve. So we can see in this region where the area is being bounded, the upper curve is the, you know, inverted parabola, 12 minus x squared. That's my upper curve, right? And then my lower curve, so again, in this particular region, my lower curve is the green curve, x squared minus 6. All right. Now, I want to point out to you that if I'm out here in these x values, the upper curve is the parabola x squared minus 6. The lower curve is the parabola 12 minus x squared. But we're not considering area in this region. We're not considering area in this region. And then, you know, ditto over here. We're not considering area in this region because in this region, the upper curve is x squared minus 6. The lower curve is negative x squared plus 12, right? We're only looking in this region. And in this region, we can see from this intersection point, the negative x squared plus 12 is the upper curve. All right, so we need to find these points of intersection. Keep in mind, excuse me, how we find points of intersection is we set the equations equal to each other. So to find those particular points of intersection, I'm going to take 12 minus x squared, and I'm going to let that equal x squared minus 6, and that's going to find my points of intersection. So I'm going to add this x squared over here, and I'm going to add this 6 over here. I'm going to divide both sides by 2. Right, so, you know, keep in mind, in this particular example, I don't have an x to the first power. So I'm able to isolate the square function and square root both sides. Right? If I had an x to the first power in here, I would most likely need to set everything equal to 0 and then factor or use the quadratic formula. Maybe we'll look at another example similar to that in just a moment. So what we have then is 3 and negative 3 as my intersection points there. So those are going to be my limits of integration, negative 3 to 3 for that bounded region of area. All right, and that technically should be the new concept for you in this conversation. Evaluating this integral is something that we've done before. Well, let's go ahead and work through it for some practice, right? So I would distribute the negative here, and I have a negative x squared minus x squared is minus 2x squared. And then I would distribute the negative here and get a plus 6. 12 plus 6 is positive 18, right? So now I'm integrating this polynomial, and then I'm going to evaluate each term. So I'm going to have, you know, the negative 2, the integral of x squared, plus, you know, I like to pull the constant out and integrate in that manner. right? Excuse me. So the integral of x squared is 1/3 x cubed. And then the integral of 1 is x. And I'm going to evaluate all of this from -3 to 3. Right, so I'm going to have to plug in and evaluate upper minus lower. Right, so I'm going to take the upper limit, plug it in, and then subtract with the lower limit plugged in. Right, so I'm going to have -2/3. I'm going to have 3 cubed plus 18 times 3. So, there's my upper limit, and then minus my lower limit, I'll have -2/3, -3 cubed plus 18 times -3, and then we're going to simplify all of this here. All right, so I have 3 cubed is 27, divided by 3. And then times 2, right? So I have, if you think about this for a second, right, here's 3 cubed divided by 3, that's 3 squared. So 3 squared is 9, times 2 is 18, so I got -18. And then I have 18 times 3 is 54. I don't know why that keeps popping up on me. And then same thing here, right? I have basically, I could factor, I get -1 cubed, which is -1. I could pull that out, I get positive, and then I'm subtracting that. And then again, so I got 3 cubed over 3, that's 3 squared, which is 9 times 2, which is 18. And then again, I got 18 times 3 is 54. This is -54, and then I'm distributing this negative, so that's +54. And then I have, what's -18? -18 is -36. And then I got 54 plus 54, which is 108. And then 108 minus 36 would be 72. All right, so we're finding area between curves. And the area between these two curves is 72. And remember, area is square unit. So we weren't told any units here. Those were feet or inches on that y-axis. But whatever those dimensions are, meters, kilometers, right? I'm going to have square units there. So again, visually, right, let me scroll back up for a second. What we were looking at is the area between these two parabolas, right? So we found the area bounded by, right? So we had to graph the -x squared plus 12, we had to graph the x squared minus 6 and visualize what was bounded between the curves. Now, a lot of students will ask a really good question. They'll say, well, why didn't we consider this area out here? Well, we think about this for a second. As these functions continue forever and ever, this area out here is going to be infinite. So for the moment, we're not even going to consider area that's infinite. That doesn't make any sense to us, right? And again, as this function continues forever, ever, and ever, and this function continues forever and ever and ever, this area between those two curves is infinite. So it doesn't make any sense for us to find the area between those sections of the curve. That area would be infinite. So you'll see typically the instructions involve saying something like area bounded by the curves, and what they mean is the finite area between the two curves. Okay. So there's one example there. Now let's take a look at a slightly different example. And in this scenario, what I want to do is let's consider like an oriented version of functions, right? So what I mean by that is let's suppose we had functions that look like this. So let's say we had x equals f of y and x equals g of y. So conceptually speaking, this is the exact same concept. We're going to look at the area between the curves. Now if you think about this, the width of the rectangle, if you will, is a delta y. So we're going to have, upper curve minus lower curve. And, what most textbooks do is they talk about like it's really the rightmost curve. That's what we would consider upper here. Why do we consider that upper? Right? Well, good question. Well, think about, let's say, this is a larger number. Right? This x value, right? This x value is a larger number. And this x value is a smaller number. right? This x value is smaller, right? So when we do larger minus smaller, that gives us a positive measurement for the area between the curves, right? So you typically see something like this: f at y minus g at y, right, notationally, and then we have a delta y as the thickness of our integrals, right? And usually most textbooks will say this is the lower limit of c, this is the upper limit of d, and those will be our limits of integration. So conceptually, the same exact thing that we did in our first example. We're finding the area between two curves, but in this case, the curves are functions of y. So let's look at a specific example related to that scenario. So let's suppose that we want to find the area bounded by, let's say something like this. Let's say we have x equals y squared minus 4y, and then we have, let's say, x equals 2y minus y squared. Or now look, we could sketch these by hand as well, right? Think about this. If we set x equal to 0, then we could find the intercepts here. Right? And if we set x equal to 0, we could find the intercepts here and graph those. So we would factor out a y. So we'd have y equals 0 and y equals 4 as the intercepts for that graph. And if we factored a y out here, we'd have a y equals 0 and y equals 2 as the intercepts there. So we could sketch this by hand by finding the intercepts for that function. What I'm going to do is cheat a little bit. Let me use my technology. So let's say I want to graph this on my graphing calculator. I'm going to point out to you that if I hit y equals, what we have to have is y equals functions of x, and that's not what we have. We have x's equal to functions of y. So here's a quick little workaround for that. So I'm going to hit my mode key, and I am going to arrow down here. Notice we're in function mode. What I'm going to do is switch to parametric mode. And when I do that and I hit the y equals key, you can see I now have groupings of equations. Right? And so here's the short workaround. Notice in this form, the y is like the independent variable, right? And the x is dependent upon the y. So what I'm going to do is I'm going to let y be the independent variable. And the way I'm going to do that is I'm going to come over here. I'm going to come down to the y equation, and I'm going to let y equal the variable. So when I'm in parametric mode and I hit this key, you can see it's giving me the t variable. So I'm in function mode, it gives the x. I'm in parametric mode, it gives the t. I'm in polar mode, it gives the theta. And I'm in sequence mode, it gives the n. Right? So we're in parametric mode, it puts the t there. And then my first equation, what was my first equation? Y squared minus 4y. So I'm going to do the t squared minus 4t. So if you think about this, right, if I did like a substitution, if you will, right, if y equals t, when I sub t equal to y, I get y squared minus 4y, and that's the equation we have there. So this is a cool little workaround for graphing x's as functions of y. So I'm going to do the same thing for the second equation. I'm going to come down to y. I'm going to let that be the parameter t, and then I'm going to graph 2t minus t squared, and that should give me those graphs. And I'm going to graph and then show you something we need to fix. So when I hit graph, here's the two parabolas, and I want you to point out to you this is only like a portion of the parabola. This is only a portion of the parabola. So here's what your calculator does. Its default, if I go into the window, its default is to let the t-min be 0, the t-max be 2 pi. So remember, the t's are my y values, so it's starting the y values at 0. And if we look back at our graph, notice the y values begin at 0 and they move up. So I'm just going to go back to the window. Let's make this like, let me use the negative key, negative 10 to say 10. And then when I graph, that should give me a more complete picture of the parabolas. So I can see here's one parabola, here's the other. Now if we think about this for a second, algebraically speaking, this parabola has a positive y squared, so that's going to be this graph opening upward, right? And this parabola has a negative y squared, and that's going to be this graph opening downward. And if you keep this in mind on my calculator, I can hit trace, and I can hit my right arrow. Oops, my right arrow. Now here's what it's doing. It's tracing as t increases. So let me move a little quicker. And as t increases, there's my curve opening up, right? So that was this curve right here, y squared minus 4y. And we can see that one there, right? There's the parabola opening up. So if we look at the region bounded between these curves, I'm looking at the rightmost curve and the leftmost curve. So the rightmost curve is this parabola opening down. And then the leftmost curve was this guy right here, which is the y squared minus 4y. So my rightmost curve is 2y minus y squared. My leftmost curve is the parabola opening up. And then I just need to find these points of intersection, and that'll tell me the y coordinates where they intersect. All right? So again, let me sketch this real quick. Calculator go away. Right? So let me sketch. Roughly, we had, let me bring that guy back up for me, right? We had, looks like an intercept at the origin. And then again, you know, we talked about this, right? Let's point this out to ourselves. If I factor a y out of here, I get y minus 4. So we can see for this graph, y equals 0 and y equals 4 were those intercepts, right? Here's 0 and 4 as those intercepts. So 0 and 4 as those intercepts, and that guy looks roughly something like this, right? Here's y squared minus 4y. Let me switch to red. And again, you know, if I think about factoring a y out of here, I get 2 minus y. So we can see y equals 0, y equals 2 is the intercepts for that graph, right? So we can see y equals 0 and y equals 2 is the intercepts of that graph. So here's y equals 0, y equals 2, and roughly something like that. Wow, that was a horrible sketch. All right, so I'm looking for the area between those curves, right? So what I need in this case is that y value and that y value, because that's what tells me where the curve is bounded, okay? So again, I'm going to have, let's say, the rightmost curve minus the leftmost curve, and these are functions of y. So we said our rightmost curve was 2y minus y squared, and then my leftmost curve was the y squared minus 4y equation that we talked about, right? And then my y limits of integration are from 0 to 2. Oop, nope, oh my gosh, that is totally wrong. All right. Let me get ahead of myself here. So the bottom limit of integration is 0, but the upper limit of integration is that intersection point. I almost made a mistake there. Right? So we need the points of intersection. So I'm going to set these two curves equal to each other. I'm going to set 2y minus y squared, just like we did in the prior problem, equal to y squared minus 4y. So I'm going to add this to the other side. And since we have a y variable, I'm going to subtract this to the other side. And I'm going to set this equal to 0. So I can't just square root both sides of the equation in this case. So, you know, I'm going to have, I'm going to take out the common 2 as well. So I'm going to have y minus 3. Oh, dang it. I'm taking out a y as well. So I have a 2y here. Let me make that look a little prettier. So setting the two curves equal to each other, we can see we're going to get y equals 0 here. We're going to get y equals 0 here, and we're going to get y equals 3 as the points of intersection. Right? So this is y equals 3, and this is y equals 0. So there's my upper limit of integration. And then we have the dy as our variable of integration. All right. Look, I'm going to stop here. I'm going to assume you could finish this problem off. Right? I have negative y squared minus y squared would be minus 2y squareds. And then I'd have 2y plus 4y is 6y. And then I would evaluate the antiderivative, right? So I'd get a y cubed over 3, I'd get a y squared over 2, and then I would do upper limit minus lower limit, and I would finish that problem off there. So conceptually speaking, if we're finding areas between curves, we can have areas that are y's as functions of x. We could have areas where x is a function of y, and it's the same concept, right? So we're going to have, let's say, upper minus lower, or we're going to have right minus left in regards to the area bounded by the curves. All right, let's take a look at one last example where we might have, let's say, an application of this concept. All right? So one last example here. And let's look at, well, let's consider something like a word problem. So let's suppose we have a lake shown with distances across the lake measured at, let's say, half mile intervals. So I'm going to sketch a lake. Let's say my lake looks something like this. And let's say we have measurements of the lake at half-mile intervals. Right? So let's say I'm going to draw this to where it looks kind of decent. So let's say at this measurement, the lake is 1.2 miles. Man, this marker hates me. If computers could hate, it hates me. Okay, and then we have, let's say at this measurement, we have that the lake is 1.4 miles. Goodness gracious. All right, 1.4 miles. And then let's say at this length, the lake is 1.6 miles wide. And then let's say at this distance, we have, let's say, 0.6. And then let's say at this distance we have, let's say, 0.7. And then let's say at this distance we have, let's say that's 0.5. And then let's say we got one more measurement. Let's say we have this guy right here. And let's say that's also 0.5. So we have some measurements of our lake, our distance across our lake. And that came out really sloppy. I apologize for that. Right? Now we were told that the intervals between these measurements were half mile. Right? So we have, let's say, a half mile between those. Right? A half mile between those, so on and so forth. Right? We have a half mile between those as well. So we want to measure, let's say we want to estimate the area of the lake. So, conceptually, as we're going to do, we're going to consider this as like area between curves, right? So we're going to kind of suppose that, let's say, this is the lower curve, right? And then we're going to consider, let's say, this is the upper curve, something like that. Suppose there's my upper and lower. So this is the height of, let's say, the rectangle. And this is the height of the rectangle. Right? This is the height of the rectangle. If we're going to use rectangles here. Right? Let's suppose the instruction said something like this. Let's suppose the instruction said use approximating rectangles with midpoints. With midpoints to estimate the area of the lake. See, with midpoints to estimate the area of the lake. All right, now I am coming back up here for a second. I'm going to switch to a different color. I want to try to distinguish here what is what. All right. Now, what I'm going to do personally, I'm going to consider, let's say, right here, this is the 0 mark. So let's say we have an area of 0 between those curves there, and we have an area of 0 between those curves there. So what I'm going to envision is like, here's my first rectangle. And then this is my midpoint of that rectangle. And then I'm going to consider this like the second rectangle. And then here's the midpoint. Again, I'm using this and this as the distance, the midpoint. I'm using this and this as the distance, right, the midpoint. And then I'm using this as my midpoint. So here's my other rectangle here. So that's my midpoint. And then last but not least, I have this guy here as my midpoint. So you can see that the 1.2, the 1.6, the 0.7, and the 0.5 are the midpoints. And then when I think about the delta x, right, so if I look at this rectangle here, I have a half a mile here and a half a mile here. Here's a half a mile distance there and a half a mile distance there. So my delta x is really 1 mile, right? So my area using midpoints is approximately, I have a delta x of 1, and then the first midpoint was, oh, this is going to drive me crazy. First midpoint was 1.2 right here. Second midpoint was 1.6. So I got 1.2 and 1.6. So here's the area of my first rectangle, and then I have 1.6, and then I had 0.7, if I remember correctly, and then 0.5 as the last midpoint. Is that right? Did I do that right? Yes! That's if this thing didn't hate me and scroll really fast. So we had the 1.2, the 1.6, the 0.7, and the 0.5. So numerically, here's a estimation to the area of the lake using midpoints of the distances that were measured and given to us. Right? So, let me go ahead and take out my calculator and add these together and make sure I don't make a mistake. I got 1.2 plus 1.6 plus 0.7 plus 0.5, and I get 4. I should have been able to do that. Oh, that makes sense. This is 7 and 5 is 12. There's 1.2. This is 1.8. All right, that would add to give me 4. Absolutely. All right, so then the area here is approximately 4. Now keep in mind, we have 1 mile, 1.2 miles, so we have square miles for our estimated area. So there's an example, a quick example of how we might use areas between curves in an application.